Hello there. It's time for more statistics. Today we want to look at confidence intervals for sigma squared, that is the population variance, and for sigma, the population standard deviation. And the technique is going to be to find a confidence interval for the variance, sigma squared. Then if what we want is a confidence interval for the standard deviation, you just take the square roots of the endpoints. So we'll really be working with variance here, but easy to jump from variance over to standard deviation. So let's suppose that we want a 1 minus alpha confidence interval estimate sigma squared. Well, what is that? That would be find two numbers and right now let's call them capital A, capital B, and we want to form an interval, so we want A less than B, A is on the left, such that 1 minus alpha is equal to the probability that sigma squared is between A and B. Now, all we need to go from there to finding the values for A and B, if I find the values for A and B, that is a confidence interval. We need a little bit of elementary probability and elementary algebra. So really, I'm not exaggerating, these are elementary, but they're really keen applications of probability theory and algebra. So let's go ahead and start this and see if we can't figure out a confidence interval. So we're going to start with the statement 1 minus alpha is equal to the probability that A is less than sigma squared is less than B. Now what's inside the parentheses here is an inequality, and there are several things we can do to inequalities, this would be algebra, that will change the form of the inequality but not the value of the inequality. And for example, if we would take reciprocals, then we would have to reverse the inequality signs, but the description would be of the same set. And all I'm saying there is, now I'm going to replace this inequality with something equivalent, and that would be 1 over A greater than, notice that was a less than, now it's got to be a greater than, 1 over sigma squared greater than 1 over B. All right, that's just elementary algebra. Now, it's more usual for us to write an inequality in probability theory in this way with the less than, less than. Notice I can just rearrange this because I can read this from left to right or right to left. So I can just rewrite that as the probability that 1 over B is less than 1 over sigma squared is less than 1 over A. So instead of writing it left to right, I've written it right from left. Read it here. 1 over B is less than 1 over sigma squared is less than 1 over A. So that's equal because it describes exactly the same event. Now what I'm going to do is to multiply each member of the inequality by the same thing, and that doesn't change the inequality. So I could multiply by 2, multiply by 2, multiply by 2. The set described here would be the same, and so the probabilities would be the same. Now I'm not going to multiply by 2. I'm going to multiply by n minus 1 s squared and then the b that was there is still there, less than n minus 1 s squared over sigma squared. Now if I multiplied the first term by n minus 1 s squared, then I've got to multiply the second term by the same thing, and for the third term, same result, s squared over sigma squared, and close the paren. So these are all equal to 1 minus alpha. Now, why have I got here? I mean, I hope you can see that I can get here, but why? Well, if I've taken a sample of size n, then a result from the textbook, which I'll just label result, is that n minus 1 s squared, where n is the sample size, s is the sample standard, well, this would be sample variance, and sigma squared, that would be the population variance, and this has a chi-square distribution with n minus 1 degrees of freedom. And this would be something that we looked at briefly last week. And a sketch of this chi-square distribution, just as a reminder, it's not the first time you've seen this. This will be a little piece of the real number line. And the chi-square distribution is different from the t and the z in several obvious ways. It's not symmetrical. It's not negative ever. It extends from 0 to the right, so only positive values under the chi-square probability density function. There are many chi-squares, and we use the parameter degrees of freedom to tell them apart. So this would look like a chi-square with, 7 or 8 degrees of freedom. The higher the degrees of freedom, the more this humpy part here migrates toward the right. So again, that's review. We have learned all that. Now what is new is that this expression will have a chi-square distribution with n minus 1 degrees of freedom. We do rigidly require that the underlying population have a normal distribution. Now that was when we were working with the mean, that requirement was somewhat flexible. It's not flexible when we're working with the chi-square. The underlying population really needs to be normal. Okay, now since I know this is chi-square, let me pick up right here and say that that expression is equal to the probability that n minus 1 s squared over b is less than a chi-square random variable with the appropriate degrees of freedom, n minus 1 s squared over a. Which means that from this chi-square distribution, we want to chunk out a piece in the middle, left boundary, right boundary, so that the area between the left boundary and the right boundary is, follow these equals back, is 1 minus alpha. Now, in pictures, that would maybe look like this. Let me get some pretty ink here. This would be a left boundary right there, and this would be a right boundary. And the area would be alpha by 2, and the area down here would be alpha by 2. Now, just maybe some of you are going to say, you know, what we've got here is an area of 1 minus alpha in the middle, but it looks like there'd be more than one way to pick off that area 1 minus alpha. And you're right. If you say that, you are right. But it just makes all kinds of sense to take the missing area and divide it evenly between the two tails. And that's what we're going to do. And this point right here would be a critical value. And we would call this, I'm going to use a slightly different notation. This is a critical value for alpha by 2, so it cuts an area of alpha by 2 in the upper tail. But, you know, maybe it is easier, your author certainly adopts this notation, to call it chi-square r. That would be a critical value. I guess I could even add alpha by 2 if I wanted to. That's a critical value that cuts an area of alpha by 2 in the upper tail. So this is a critical value. The r means on the right-hand side. And this one over here, we've not really had a notation explicitly for this point, but this would be called chi-square left, and then an alpha by 2, even though we'll often assume that people know we're talking about alpha by 2 and omit that. So chi-square right, chi-square left are critical values under the chi-square curve on the left and the right. Now, what's the defining property of chi-square r? Leaves an area of alpha by 2 in the upper tail. That would be what in this inequality this point is doing. We're capturing in the middle an area of 1 minus alpha, so in each end we've got an alpha by 2. What I'm getting at is that therefore chi-square right is equal to n minus 1 s squared over a, and that would mean that a is equal to n minus 1 s squared over chi squared right. Now, before I scroll, let's remind ourselves what A and B actually stand for. We wanted an interval, A being the left-hand endpoint and B being the right-hand endpoint. So what we found is left-hand end of the confidence interval. We found the left-hand end of the confidence interval. And to find the right-hand end, we would note that chi-square left end, this is a critical value over on the left-hand side, would be n minus 1 s squared over b, so that b would be equal to n minus 1 s squared over chi squared left. So now we know our 1 minus alpha confidence interval estimate of sigma squared is, now B is on the right, A is on the left. The interval is A to B, so this is going to be n minus 1 s squared over chi squared, just read here so we don't make a mistake, chi squared r, comma, n minus 1 s squared, numerator's the same, chi square l. And I've written that several times because I want you to remember, you can understand also because we've derived the whole thing, but remember that the right-hand critical value is the denominator of the left-hand endpoint. The left-hand critical value is the denominator, thing in the bottom, of the right-hand endpoint of the 1 minus alpha confidence interval. Now, we derive this only once, and then here's the result, and we can use this. And so why don't we do problem 17 out of our text, page 371. And this problem is about pre-1983 pennies and their weight. So they want us to take a sample, n equal 40, and get a 98% confidence interval estimate of sigma, not sigma squared. But remember, we're going to have to find a confidence interval for sigma squared, and then we'll know the confidence interval for sigma by taking the square roots. Okay, so I would think this would probably be fairly easy to do. We've got a sample of size n equal 40, and that's in the appendix of our book. And that sample, let me flip over to Minitab and show you what that sample looks like. So these are Indian pennies, wheat pennies, pre-1983 pennies, and what did I say, pre or post? Actually, I'm going to be using the, I could use pre, but I did this earlier and used post. Yeah, I used the modern ones. Post. We changed the composition of the pennies in 1983, and so the weights are different for pre-1983 than they are for post-1983. So here are our post-1983 pennies. Now let's find the number of post-1983 pennies we have, and I'm reading here. I'll get this up where you can see it a little better. Here's post-1983 pennies. It looks like there are 37 in our sample, and so that would be degrees of freedom of 36. So we've got 37 in the sample, so 36 degrees of freedom. You just have to remember that with me and help me, remind me as I forget. So we've got, let's go back here and scratch for just a second. We've got, it actually wasn't n equal 40, it was n equal 37. So our degrees of freedom is equal to 36, and the chi-square we want would be a chi-square it'll look like this. I'm exaggerating that a little bit for us. Chi-square degrees of freedom equal 36. We want an area of O1 in the upper tail and an area of O1 in the lower tail, because we want a 98% confidence interval. So in the middle we'd have 98% of our data. That looks okay. We need to find these critical values. Minitab will find those critical values for us, and let's whip over and let Minitab find those for us. So I think today we'll use the graphing approach to finding those. We'll plot probability distribution, and what we want is to view the probabilities. So we'll say OK. And then we want a chi-square distribution. I've already got that selected, chi-square. The degrees of freedom, our sample size was 37, so our degrees of freedom would be 36. And the shaded area we want on both tails, so that icon is selected. And the probability, that is, how much is the shaded area? And altogether it's O2, so we've got that in the probability. And we'll say OK. And here is what our distribution plot looks like. Now you can see this is not symmetrical. It's not as skewed as I drew it. I drew it skewed to emphasize the skew, but it is skewed right. This longer tail points over to the right. It starts at 0. There are no negative values. And this critical value on the left is 19.23. I'm writing these down. And the one on the right is 58.62. 58.62. So let's go back to the graphics tablet with those values. And what we know now is that this critical value over here is 19.23. 19.23, emphasize the point, and 58.62. And I think we can afford to scroll up a bit here. So our 98% confidence interval is, and this is for sigma squared, don't forget, is going to be n minus 1, which would be 36, s squared. Did we get that? I'm afraid we didn't get that. So real quick, we've got to figure out s squared. So let's do stat, basic statistics, descriptive statistics. Got the right data set. The statistics we want are mean, standard deviation, n total. I think that looks okay. We'll say okay again. And Minitab says 37 pieces of data. This looks better. With a mean of 2.4991. We don't need that. But a standard deviation of 0.0165. And we do need that. 0.0165. That's the standard deviation. You know, we could have had Minitab give us the variance also, but we're okay. 0.0165 squared, and this would be the critical point from the right-hand side, 58.62, comma, 36.0165 squared over the critical value from the left, 19.23, being big, parens like that, and we'll want to know what that is. And so we will find our calculator, and that's going to be 36 times 0.0165, and that would be squared, and then divided by 58.62 is 0.00017. I know this got kind of small number, didn't it? Now calculate this value. Okay, then I've got it in my calculator. So all I need to do is to change the denominator, since the numerator stays the same, 19.23, and this is 0.0051. 0.0051. Decimal point right there. But that's a confidence interval for sigma squared. 98% confidence interval for sigma, that's what we were asked to find, is we have to take the square root of 0.00017 up to the square root of 0.0051 is equal to the square root of 0.00017 is a 0.013, And just one more. The square root of 0.00051 is 0.023. 0.023, and that would be grams. So this is a 98% confidence interval for sigma. And I think if you'll watch that twice, you'll see how you get the confidence interval, which is more important than how you derive the confidence interval, but I didn't want to leave you with the impression that that was magic. Far from it. Okay, that's all that we have to say right now about a confidence interval for sigma and for sigma squared. Practice, practice. You'll find some problems assigned in your textbook. Thank you.